So anybody has any difficulty in momentum flux, heat flux, and mass flux, molecular transport? Molecular transport means conductive transport. So we have discussed three laws: Newton's law of viscosity, Fourier law of heat conduction, and fixed law of diffusion. Then we got some transport property, common transport property, that is called as a diffusivity, which is derived from viscosity, thermal conductivity, and diffusivity in mass transfer. So common diffusivity. And then we got three-dimensional less number, Prandtl number, Schmidt number, and Lewis number. Primarily, this Prandtl number signifies simultaneous momentum transfer and heat transfer. Schmidt number signifies a simultaneous momentum transfer and mass transfer, while Lewis number signifies simultaneous heat transfer and mass transfer. So based on value of Lewis number and all, so dimensionless number is very important. So and that time I told you, most importantly, you remember all the properties of air, at least air and water, or nitrogen, oxygen, and water. So these are you can say kind of basic components of chemical engineering. So water, and then oxygen and nitrogen. You should not give any excuse that you don't know these properties of these three compounds. First of all, oxygen, nitrogen, and average property will be of air. Similarly, in liquid, water. What at least that you should remember all the properties. Okay, so we got the magnitude of this dimensionless number, Prandtl number, Schmidt number, and Lewis number for gases. So magnitude will be approximately 1, while for liquids, Prandtl number 10, order of magnitude, and Schmidt number is 10 raised to 3, while Lewis number is 10 raised to 2. So anybody has any difficulty, any confusion over this? So now we'll move on. We'll move on to convective flux. So what is the definition of convective flux? Yeah, anybody in a class?
Yes, sir. It arises from bulk flow or fluid motions.
Very good. Bulk flow. So when there is a bulk flow or flow motion, so have you heard of convective flux before? Who was that? Roll number? Can you tell me your roll number?
109, sir.
109. Okay. Have you seen any convective flux anywhere?
No idea, sir. Like,
No, but so you might have studied somewhere, no? Convective flux. It's a sham.
yes, sir.
Yeah.
In fluid motion,
Yeah.
we cross like when we go for buoyant force,
Mm-hmm.
we use a convective flux.
Very good. So do you remember what kind of
And in heat transfer also, sir.
heat transfer? Heat transfer, what kind of formula? Where you have come across this convective flux?
Near those
Heated surface.
heated surface and the releasing of heat, sir.
Yeah.
The releasing of heat, that
So
place.
hot pipe is there, and there is a heat transfer, and so air in contact with this hot pipe is moving. So there is a bulk motion, hence that is called as a convective flux. So do you remember what law you are using heat transfer? How you have calculated heat flux in convective flux in heat transfer? Roll number 97, Sridhar.
Yes, sir. For convective flux, we use Q equal to H delta T.
H into delta T. So H is a heat transfer coefficient.
It's for coefficient. Yes, sir.
Okay. So everybody knows this. Convective flux is H into delta T. Anybody don't know? Okay. So I will tell that is altogether wrong. Fundamentally wrong. H into delta T is a not convective flux. So Sridhar.
Yes, sir.
So where is the bulk motion? H into delta T. How bulk motion is accounted in there? H into delta T is a convective flux. And definition of convective flux is telling me that there should be bulk motion involved in there. Then only I can
Yes,
call
sir.
it as a convective flux. So where is the bulk motion in H into delta T? Yeah, roll number 77, Tejas. Tejas.
Yes, sir.
Yeah. Where is the
Separate
bulk motion involved in H into delta T? H. What is H? You know?
transfer coefficient.
So where is the bulk motion involved when I am calling H into delta T is a convective flux?
So in Newton's laws of cooling, we have it.
Yeah, Newton's law of cooling is there. So where is the bulk motion? Definition of convective flux is there should be bulk motion in convective flux. Now, this is one statement is when there is a bulk motion, I will call it as a convective flux. Now, second statement is H into delta T, which is Newton's law of cooling, gives me a convective flux in heat transfer. So, where is the bulk motion in H into delta T?
Moving liquid or gases. Mm,
Okay, liquid or gas, but which property? Whether delta T is representing bulk motion or H is representing bulk motion?
bulk temperature of the surrounding fluid, that, yeah.
That is representing bulk motion.
Kind of.
Yeah, roll number 51. Himanshu.
Yes, sir.
So, what is the characteristic property? If I want to call there is a bulk motion, there is no bulk motion. So, how you will represent bulk motion? Characteristic property, fundamental property, which is used to represent the bulk motion.
So velocity of
Very good.
particles.
Very good. Velocity of the particle. Okay. Moment of the particle or moment per unit time. That is velocity of the particle. And where is bulk motion coming in H into delta T?
So driving force is temperature, but in heat mass transfer coefficient carries the characteristics.
Yeah. So overall heat transfer coefficient is a function of velocity.
Yes, sir.
Is it so?
Yes, sir.
How? Do you
Sir,
remember
it
any
depends.
relation
Sir,
between
H
velocity? Any
depends on
relation
the
between?
property of the substance which we carry. H
No,
directly depends on
H
that.
is not a property of substance. H is a property of system.
Yes, sir.
It doesn't depends upon a substance. It depends upon whole system and surrounding. Everything will have effect on heat transfer coefficient. So, do anybody remember how H is related to velocity? What is the relation between H and how it is related? Roll number 21, Sai.
Yes.
Yeah. So, how H is related to velocity?
Uh, Sir, it is like a convective heat transfer coefficient uh,
Very good.
relating with
So, how H is related with velocity? Yeah, anybody else?
Excuse me, sir.
Yeah, tell me. Roll number
4, sir.
4. Yeah, tell me.
So more the velocity, more the heat transfer coefficient. But if the velocity is more, the pressure drop will be also more. So we have to take account of pressure drop also. So like,
Okay. So you are correct actually. More the heat transfer, more the velocity, more is the heat transfer. So have you heard of any equation relating this, Aditya?
sir, I'm not able to recall, but we have studied in advanced heat transfer actually, the relation.
Okay. So mm, have, any because I know everybody knows the equation. Everybody knows the equation. Only the thing is that is also main aim of this transport phenomena. You know the transport phenomena. Only just I am trying to uh, tune you in such a that at correct time you should use correct equation, because I know everybody knows how heat transfer is related with velocity. Only the thing is I'm asking in different way. Okay. So if I ask you how Nusselt number is related to Reynolds number, so everybody will remember. How Nusselt number is related to Reynolds number, Aditya? Nusselt
So
number is
Nusselt number is equals to Reynolds number to power 0.23 into Prandtl number to power 0.3 or 0.4, depending upon the cooling and heating.
there you can see now Nusselt number will have heat transfer coefficient and Reynolds number will have velocity.
Velocity, yes, sir. Yes,
So
sir. Yes.
that is the equation, I think, and almost everybody might have been used that equation hundreds of times. Debtors-Boelter correlation or flow over flat plate or everywhere. It is different for different systems actually. So that is what, if some question is asked in some different way, you should not get bothered. So you should stick to your fundamentals and just recollect all the information what you have studied previously and try to correlate. So whether somewhere heat transfer coefficient and velocity is correlated. If I say what is the relation between Nusselt number and Reynolds number, so you can tell that okay, Debtors-Boelter correlation is there, Whittaker correlation is there. So many correlations are there. But if I am asking that heat transfer coefficient and velocity, so you got confused. That should not be there. Okay. So moreover, I'm telling that is not the convective flux only. H into delta T is a total flux. Okay, total flux. So whatever that is fundamentally wrong, telling that H into delta T is a convective flux only. It is total flux. But what is happening, that is in a way correct also. In a way correct means if I am considering convective flux in association with molecular flux, if both fluxes are there, wherever there are convective flux and molecular flux, most of the time it will be dominated by convective flux, because this characteristic of convective flux is bulk motion. Certainly if you have bulk motion, fluxes will be higher. Say if I somewhere a flux is 100, so 99 will be convective flux and only 1 will be molecular flux. So whenever there is a convective flux, so the molecular flux will be negligible. So H into delta T is not a is not a convective flux. H into delta T is a total flux, which is addition of convective flux plus molecular flux. But most of the time it is referred as a convective flux. That is fundamentally wrong, but in a way it is correct, because in that case flux is dominated by convective flux. Okay, whenever there is a convective flux, a total flux will be dominated by convective flux. When there is no convective flux, then only you can say molecular flux have some role to play. As soon as there is a convective flux, so total flux will be dominated by convective flux. That is one way. So whenever there is a convective flux, so overall total flux will be dominated by convective flux. Hence H into delta T, and similar equation in momentum transfer, similar equation in mass transfer is referred as a convective flux. But that is fundamentally wrong. That is not a convective flux purely. Okay, purely convective flux is the velocity and flux, bulk motion. Okay, bulk motion is characterized by velocity. So this convective flux, so bulk motion, as somebody pointed out very correctly, it is characterized by velocity. So what should be the remaining term? If I want convective flux and velocity is the integrated part, so what should be the another component? Velocity into some term which will give me flux.
So,
Yeah.
sir, it should be quantity per volume.
Very good, very good. And this already we have discussed. It will be quantity per unit volume multiplied by velocity is a convective flux. Okay, quantity in per unit volume into velocity. So quantity per unit volume into velocity can be represented like quantity per meter square per unit time. Okay, quantity per unit time per meter square. So it will be a quantity per unit volume into characteristic velocity. So characteristic velocity, just don't get confused velocity with characteristic velocity. It depends upon situation to situation. Sometimes we will have multi-component system. Sometimes we will be mixing with two streams with different velocity. Sometimes some concentration of one stream with lesser momentum is more. And this characteristic velocity is the property which is defining the velocity, particular velocity, particular, you can say particular for a given system. Okay, so quantity per unit volume. So quantity per unit volume in momentum transfer. What is quantity per unit volume in momentum transfer? What is quantity per unit volume in momentum transfer? Ravi, roll number 40.
Yes, sir.
Quantity per unit volume in momentum transfer.
Sir, it is shear stress, sir.
Quantity per unit volume. How can you prove?
Sir, the quantity that is changing in momentum transfer is.
I am asking about quantity per unit volume. Quantity. So you are telling that momentum per unit volume is a shear stress.
Yes, sir.
How?
Momentum into momentum is mass into velocity by uh, uh, no, sir, I'm mistaken.
So quantity per unit volume is?
So it would be density into velocity.
Very good. Density into velocity is a quantity per unit volume. Momentum per unit volume in momentum flux. What is the quantity per unit volume in heat transfer? Yeah, roll number 50, Rashmi.
Yes, sir.
So heat per unit volume.
So it will be rho into CPT.
Very good. Rho into specific heat into temperature will represent the heat per unit volume in heat transfer. What is the mass per unit volume? Roll number 71, Himani. Roll number 71, Himani.
Yes, sir.
Yeah. Had your breakfast?
Or it will be that mole
Yeah. So what is
concentration.
concentration? It is concentration. So you had your breakfast or doing your breakfast in class timing?
No, sir, I have cold and fever. So
Okay, it's fine. So density into velocity is a momentum per unit volume into velocity. So density into velocity is a convective momentum flux. Okay. Similarly, rho density into specific heat into temperature into velocity is a convective heat flux in heat transfer. Similarly, concentration, simply concentration into velocity is a convective flux in mass transfer. Okay, so this, as I told, for characteristic velocity, this is for quantity per unit volume. Quantity per unit volume I got. So sometimes you will have multi-component system. Sometimes you will have say some gas liquid mixture and everything. So velocity, accordingly you need to select the characteristic velocity which will represent a effective bulk motion. So there all your subject knowledge will come into picture. So how you are dealing thermodynamics, how you are dealing fluid mechanics, how you are dealing this heat transfer. So accordingly you need to judge a suitable way where you can get the multi-component system, velocity in multi-component system, even though it is not a distributive property. Velocity is not a distributive property. So you need to describe appropriate weighting factor so that as individual component will have some effect of bulk motion, effect on bulk motion and effect of bulk motion. So component will have effect of bulk motion. So convective flux is an effect of bulk motion, and multi-component system, every component will have effect on bulk motion. So this depends upon situation to situation. You need to discuss a suitable weighting factor. This is simple weighting factor is given how. So say this is the individual velocity I will define first of all, individual velocity, and then this will be a weighting factor, and this is the some arithmetic summation of this velocity I will get, and that will give me a characteristic velocity. So say for example, BI is a weighting factor and VI is a velocity of individual constituents. So whatever the constituents, okay. So commonly used this weighting factor is mass fraction or mole fraction. So mass fraction or mole fraction, and this is what I will get individual velocity. Individual velocity. So summation. This is just one example given. Okay, this is just one example given. So what is the best weighting factor and individual velocity? How to? Because as I told, convective flux will have effect of bulk motion, and individual component will have effect on bulk motion. So this off and on is very important. How bulk motion is related to convective flux and how individual component is related to bulk motion. So that is what you need to observe accordingly from situation to situation. This is just one example given. So this I will represent individual component with velocity vi, and this is a weighting factor mass fraction, and this total velocity will be summation of individual velocity into weight fraction, and this is the mole fraction. So you can define your own way. You can have your own weighting factor. Only the thing is that time you need to study properly how individual component will affect the bulk motion and what is the effect of bulk motion on convective flux. So it should properly justify your bulk motion. So whatever be the velocity you are taking, that characteristic velocity should be properly justify your bulk motion. That is why it is called as a characteristic velocity. It is it can be a simple velocity also. It can be, you can have special kind of property which will resemble similar to velocity. That is characteristic velocity. Will have same unit the distance per unit time, but it is different than velocity. But it will have individual component effect also, and accordingly you can get the characteristic velocity. So these are the two examples given. Given this mass fraction and mole fraction is a weighting factor, then individual velocity multiplied by mole fraction, you will get this. This is called as a weight average velocity. As I am telling, this is velocity. Even though you can call it as a weight average velocity, this is called as a mole average velocity, because mass fraction or mass this mass fraction is used as a weighting factor, and here mole fraction is. So this will be a mole average velocity. This is the mass average velocity. Okay, so quantity per unit volume already we have discussed. So now as I told, total flux is a summation of molecular flux and convective flux. Okay, so total flux is a summation of molecular flux and convective flux. So certainly this is the flux, this is also flux, this is flux, this is also flux. So the ratio of this flux is a dimensionless number. Are you able to hear me?
Yes, sir.
Okay. So this total flux is a summation of molecular flux and convective flux. But most of the time, whenever there is a convective flux, okay, whenever there is a convective flux, the total flux is dominated by convective flux. Hence, many a times this total flux is called as a convective flux. That is, in a way, is not wrong, but fundamentally it is wrong. You should remember this thing. Even though, so because if I am taking total flux equals to 100 and there is a convective flux, so 99% contribution will be from convective flux and only 1% will be from molecular flux. So even though you neglect this, it will have error of 1% only. So that is why total flux most of the time is referred as a convective flux. So now here the point is different, molecular flux and convective flux. So certainly this is convective flux, this is molecular flux. The ratio of these fluxes will be a dimensionless number. So what is the molecular flux? Molecular flux, generalized equation for molecular flux. Remember?
Sir,
Yeah.
transport property into gradient of driving force.
Yeah. Again, we have generalized that. Above that. Transport property, common transport property we got.
So that will be diffusivity into gradient of quantity per unit volume.
It will be diffusivity into gradient of quantity per unit volume, and convective flux is quantity per unit volume into characteristic velocity. Okay, this will be a transport property into gradient of driving force plus quantity per unit volume into characteristic velocity. This together we have more generalized equation, that is the diffusivity. Okay, diffusivity into gradient of quantity per unit volume divided by molecular flux, and this will be quantity per unit volume into characteristic velocity. Okay, everybody got this? Now this is gradient of quantity per unit volume. Okay, so gradient of quantity per unit volume. So I want to discuss the dimensionless number. What is the dimensions of gradient of quantity per unit volume? So gradient of quantity per unit volume is dCA by gradient deltas, say d rho by dV, quantity per unit volume. Gradient of quantity per unit volume, what will be the dimensions of this gradient of quantity per unit volume? So dimensions of gradient of quantity per unit volume will be a quantity per unit volume. So this is quantity at one point minus quantity at another point divided by distance. So this will be quantity per unit volume divided by length. Gradient of quantity per unit volume is nothing but the quantity per unit volume divided by length. dCA by dy. Okay, dCA by dy. So it will have a unit of quantity per unit volume divided by length. This is clear to everybody? So this gradient of quantity per unit volume, so this is summary. So this gradient of quantity per unit volume will have dimensions of quantity per unit volume divided by length. So you take down in your notes and try to justify this by using gradient of quantity per unit volume dCA by dy. dCA by dy. So dCA by dy will be CA1 minus CA0 divided by y. So that will be equals to some CAx, some concentration divided by y. So it will be quantity per unit volume divided by length. So dimensions of gradient of quantity per unit volume is a quantity per unit volume divided by length. Is this clear to everybody? Anybody has any confusion over this? So now I can summarize everything. So this is total flux. So this is total flux. This will be a molecular flux. This will be a molecular flux, transport property into gradient of velocity. This will be a diffusivity into gradient of quantity per unit volume. And this will be a convective flux. So you can see velocity, this represent a momentum, directions of momentum. So I have x velocity and how I have y velocity. So this will be a convective momentum, x momentum flowing in y direction. This will be convective x momentum flowing in y direction. So this is momentum per unit volume, and this represent bulk motion. So this will be convective x momentum flowing in y direction. So here also two directions are associated with a convective momentum flux. Similarly for heat transfer, this is the transport property and this is the gradient of temperature. And transport property is a thermal conductivity. So this is the diffusivity and this is the gradient of quantity per unit volume, that is gradient of heat per unit volume. Okay, and this is the heat per unit volume multiplied by velocity. This will give me convective heat flux in y direction. So this is convective heat flux in y direction. So similarly for mass transfer, this is in molar form, this is in molar form, and this is in mass form. So this will be concentration into diffusivity. When total concentration is constant, it will be dCA by dy. So it will be a gradient of concentration. Okay, gradient of concentration or gradient of mole fraction into concentration, and transport property is diffusivity. The gradient of concentration itself is the gradient of quantity per unit volume, so diffusivity, and this will be a Ca into Vy star. So this will be a mole average, this will be mass average. Okay, so accordingly you can get a different fluxes for different area. Okay, so now this is flux, molecular flux and convective flux. This is molecular flux. This is molecular flux and this is convective flux. So this ratio of these fluxes will be dimensionless number. Okay, ratio of these fluxes. If I take convective flux divided by molecular flux, so convective flux divided by molecular flux. So convective flux is a quantity per unit volume multiplied by characteristic velocity is a convective flux. Diffusivity into gradient of quantity per unit volume is a molecular flux. So this is quantity per unit volume into characteristic velocity is my convective flux, and this diffusivity into gradient of quantity per unit volume is my molecular flux. Okay, this is equation A. Now just I want to analyze, because I am interested in dimensionless number. So what is the dimensions of this quantity per unit volume? So as I told you, this gradient of quantity per unit volume is the difference in quantity per unit volume divided by characteristic length. So difference in quantity per unit volume is nothing but the quantity per unit volume. So difference in quantity per unit volume is nothing but quantity per unit volume divided by characteristic length. So this is how I am analyzing the dimensions of gradient of quantity per unit volume. So it will be quantity per unit volume divided by characteristic length. Everybody got this? This is very, very important because I am discussing a dimensionless number. Okay, you might have studied getting a dimensionless number in different way. So this is how looking at the system and system property and approaching towards the appropriate dimensionless number. One will be a system property. So have you studied this Buckingham Pi theorem? Anybody has gone through Buckingham Pi theorem?
Yes, sir.
Yeah. So what there we will discuss. We'll take a system property. Okay. Will this whether say density is important, viscosity is important, velocity is important. What are the system property important? And accordingly, we'll derive a dimensionless number involved in that system. Here, actually, we are going into fundamentals of system and approaching towards the dimensionless number. So this is subjected to situation. So what we are, that Buckingham Pi theorem is a universal method, and this is subjected to situation. Given a situation, so how you can approach the dimensionless number. So here I want to get, because I know convective flux have same dimension, molecular flux have same dimension. So certainly, if I want to discuss the relative value of this, so relative value of this, so I need to have ratio. Ratio of this flux will be a dimensionless number. So dimensionless number, this quantity per unit volume, this is characteristic velocity will have dimensions of velocity. This diffusivity will have dimensions of diffusivity, and this is gradient of quantity per unit volume. Gradient of quantity per unit volume is nothing but the difference in quantity per unit volume divided by characteristic length. So certainly dimensions of gradient of quantity per unit volume is nothing but the quantity per unit volume per unit length. So this is clear to everybody. Anybody has any doubt? Here roll number 32, Lihas.
No, sir.
Not clear?
Clear, sir, clear.
Clear, na? So
Yes,
now
sir.
I can substitute here. I can substitute this combining equation A and B. So combining equation A and B. So this is quantity per unit volume multiplied by characteristic velocity. This is diffusivity. And what is dimensions of this? This will be quantity per unit volume divided by characteristic length. So rearranging this equation, this will be characteristic velocity multiplied by length divided by diffusivity. Have you heard of this dimensionless number? Velocity into length divided by diffusivity. So VL divided by DAB or V into length divided by mu by rho. And similarly, in heat transfer, it will be velocity V, length L divided by diffusivity is a mu by rho. Have you heard of this dimensionless number anywhere?
Yes, sir. It is Pecklet number.
Yeah, very good. It is Pecklet number. It is Pecklet number. So generally, so this is VL divided by alpha. Alpha is mu by rho. This is Pecklet number for heat transfer, and this is Pecklet number for mass transfer. What is the Pecklet number for momentum transfer? It resembles similar to Reynolds number. Okay, isn't it? So what is this? Instead of alpha, you put mu by rho. Okay, so it resembles similar to Reynolds number, but Reynolds number has some different physical significance. Hence, that is not called as a Pecklet number for momentum transfer. Otherwise, it has a similar role to play. Okay, so this V into L divided by mu by rho. So mu by rho. So rho into V into L, dV rho by mu. So L is a characteristic length, velocity rho divided by mu, dV rho by mu. So this is similar to Reynolds number, but we'll have different physical significance that we'll see when we'll come across this interface flux actually. But only here you need to remember Pecklet number for heat transfer and Pecklet number for mass transfer. Okay, Pecklet number for heat transfer is velocity into characteristic length into uh, alpha, thermal diffusivity. Pecklet number for mass transfer is velocity into length into diffusivity. So what is the physical significance of Pecklet number for heat transfer? Roll number 24. Bandi.
Yes, sir.
Yeah, what is the physical significance of Pecklet number for heat transfer?
Right.
What Pecklet number for heat transfer is representing?
It.
Yeah. Don't switch off your mic actually.
Yes, sir.
Yeah. Tell me.
It tells about
Roll number 56, Jitendra.
Yes, sir.
So what is the answer of question?
Sir, it may be. Can you repeat question, please, again?
So whether you are sleeping or what?
No, sir. Not
I'm
sleeping.
asking what is the physical significance of Pecklet number for heat transfer? What is Pecklet number for heat transfer is representing?
Sir, product of Reynolds number and estimate number.
So I don't want to do PhD in this Pecklet number. I'm just asking the physical significance of Pecklet number. Fundamental physical significance of Pecklet number for heat transfer. If say Pecklet number is very, very high, what will be your conclusion?
Plate number is very, very high. So it means the diffusion happens in a much longer time compared to the convection.
So that is what the physical significance of Peclet number, not diffusion. Okay, so it is the here itself it is given actually here. So you can see pointer option. So here itself it is given. Both the dimensionless number represent a ratio of convective flux to molecular flux. If it is very high, so Peclet number is very high, say 100. So certainly this convective flux is dominating. Okay, if Peclet number is very low, then molecular flux is dominating. Very low means 0.01, 0.001, then molecular flux is dominating. If Peclet number equals to 1, then convective flux equals to molecular flux. So both are important. Both are important, convective flux and molecular flux. This is what the importance of Peclet number. So what is the physical significance of Peclet number? Roll number 62, Ansh, 82. Roll number 82, Ansh.
Yes, sir.
What is the physical significance of Peclet number?
Sir, Peclet number is the ratio of the heat transferred by convection to the heat transfer by conduction, right?
Very good. Then higher value of Peclet number represents?
Sir, that in comparison to conduction, the convection, it is more.
So have you heard of any other dimensionless number which is the ratio of convective flux and molecular flux, which is defined with the ratio of convective flux to molecular flux?
Yes, sir. Just a second.
Which dimensionless number is that one? Heat transfer, convective heat transfer to molecular heat transfer.
Sir, 1 second, sir. I'm trying to recall. I have heard of it. Sir, Reynolds number?
No, heat transfer I am talking about.
Sir, I'm sorry, I can't recall right now.
Oh, you should not tell this actually. You are about to appear for an interview in next semester and GATE exam is there. So generally this Peclet number is theoretically representing ratio of convective flux to molecular flux. But there is another dimensionless number which appears or which commonly defined as the ratio of convective flux to molecular flux.
Sir, Nusselt number?
Very good. Nusselt number. Okay, Nusselt number is commonly referred as a convective ratio of convective flux to molecular flux. Now, what is the difference between? So, which is correct now? Roll number 41, Mithilesh.
Yes, sir.
Which is correct?
Sir, about
Nusselt number is a ratio of convective flux to molecular flux, and Peclet number
Yes, sir.
for heat transfer is a ratio of convective flux to molecular flux. So, which is correct one?
Sir,
And why this ambiguity is coming into picture? Yeah, anybody else in a class?
Sir, like a Peclet number is correct, and Nusselt number like it is the ratio of total flux. And total flux comes in Nusselt number.
Very good. Who is it? Roll number?
23, sir.
23. So just now I explained this thing actually. Actually, people will refer total flux as a convective flux. So in a way that is correct. Why? Because whenever there is a convective flux, a total flux will be dominated by convective flux. In that way, that is correct. But theoretically, ratio of convective flux to molecular flux is a Peclet number for heat transfer. Okay, there is a slight difference. Okay, that is also not wrong. Nusselt number is also not wrong. Peclet number is also not wrong. Both are correct, but there is a slight one is a fundamentally correct, one is a physically correct. Physically, whenever there is a convective flux, total flux will be dominated by convective flux. So total flux is referred as a convective flux. That is what general terminologies in most of the literature. The total flux is referred as a convective flux. So that is not altogether wrong, because whenever there is a convective flux, total flux will be dominated by convective flux only. So total flux itself is a convective flux. But fundamentally, if you see, the convective flux is nothing but the quantity per unit volume, rho into V is a convective flux in momentum transfer. Okay, convective flux in momentum transfer is rho into V. Okay, rho into V is a convective flux in momentum transfer. Okay, so everybody is clear with this. Peclet number for heat transfer, Peclet number for mass transfer. So if Peclet number is very, very smaller than 1, then certainly your system, the molecular flux is very, very high. Molecular flux is very high as compared to convective flux. That even I don't know the case when there is a convective flux and only molecular flux is dominating. Very difficult. When Peclet number is approximately 1, this is how say you have simultaneous molecular flux as well as convective flux. Whether you need to consider convective flux for designing, whether you need to consider molecular flux for design, or you need to consider both molecular flux and convective flux for design, that will be defined by Peclet number. Say if Peclet number is very, very high, convective flux is very fast, then limiting is molecular flux. So you can design the system according to molecular flux. If say design criteria is only flux, okay, design criteria is flux, so you can design everything based on molecular flux. Certainly, as convective flux is very, very high, so it will be away from this limiting case, and accordingly your design will be appropriate for appropriate given situation. So molecular flux is very, very low, which is indicated not very, very high, which is indicated by smaller Peclet number. Convective flux is very, very high, which is represented by a Peclet number very, very high. If it equals to 1, then both are equal actually. Both are equal. So anybody has any difficulty in this convective flux? So
Hello,
this,
sir.
yeah, tell me.
Sir, can you repeat why Nusselt number is preferred to Peclet? Sorry, Peclet is preferred to Nusselt.
Look, say if I have, so whenever I have convective flux and molecular flux together, so convective flux and molecular flux together is a total flux. So you just concentrate on this. What is total flux? H into delta T is a total flux. Okay, this is represented by H into delta T, and diffuse it into gradient of quantity per unit volume. Okay, that will be a alpha by rho into this quantity gradient of quantity per unit volume is a molecular flux, and quantity per unit volume rho into Cp into T into velocity is a convective flux. So whenever there is a convective flux, the total flux is dominated by convective flux. So say I have total flux equals to 100. So 99% will be a convective flux and only 1% will be molecular flux. So I can call this convective flux as a total flux. That is 99% correct. Okay, 99% correct when I am calling total flux as a convective flux, because whenever there is a convective flux, the total flux is dominated by convective flux. Is this clear?
Yes, sir.
Okay. So,
Hello, sir.
yeah, tell me.
Sir, like total flux, I'm getting the point if Peclet number is less than 1, really, really small, then we are neglecting. But there will be an error in the calculation, right? If we
Yeah,
neglect the convective flux or molecular flux.
yeah.
Then then why are we making such
Look.
assumptions?
Now, all engineering is about modeling the physical system. All engineering. So wherever you go, So you go in mechanical engineering, you go in chemical engineering, you go in electrical engineering. So everything will talk about modeling the physical system. Given a physical system, now I want to work with physical system. I need to design a physical system. I need to upgrade the physical system. So all this engineering will deal with the physical system, and then we'll model the equation that. Say we want to design a reactor, so we got a reactor model equation. So that model equation should be as simple as possible. Okay, model equation should be as simple as possible, should give me a feasible solution. Any model equation. So given a model equation, if you have complicated model equation, it will give you multiple solution. It can give imaginary solution. So it should be as small as possible. For that purpose, you will add the assumption. Adding the assumption means you need to impartially study the system and neglect some of the parameter. Okay, you need to study the system impartially and neglect some of the parameter. Now if I am telling that Peclet number is very small, I am neglecting convective flux. Okay, convective flux is very smaller as compared to molecular flux. So I am neglecting convective flux, and whole system will be designed based on molecular flux. In turn, what I will get? I will get some error. But at the end, most of the design will have some factor of safety. That factor of safety, even though we'll add without thinking anything, but it has a good role to play to account for all the assumptions, because getting an ideal system in real life is very difficult. So ideal CSTR doesn't exist at all. So CSTR is so simple. CSTR model equation is so simple. So ideal CSTR equation doesn't exist. Ideal CSTR, okay, doesn't exist in physical world actually. There will be some non-ideality. To account for non-ideality, I will use CSTR equation. At the end, I will add some factor of safety. So whatever non-idealities are there, that will be accounted. So here also, if Peclet number is very small, so design will be based on molecular flux only. So whatever non-idealities will be there, or whatever convective flux will be there, that will be accounted in factor of safety actually.
Yes, sir. Yes, sir.
Okay, so everywhere, wherever design you will go, you will try to get as simple as possible, because if you go now, you will see correlation. Okay, there are so many engineering correlation available. So empirical equation. So give me a 5 constant and the empirical equation. Say ax square plus bx plus c, no, ax raised to 5 plus b x raised to 4 plus c x raised to 3 plus d x raised to 2 plus d x raised to 1 plus f. So I can fit anything in that equation, but that doesn't have physical meaning at all. So you don't account anything. So some scientist has told in a literature that you can fit an elephant using 5 parameter equation, empirical equation. You can fit the elephant. It doesn't mean that 5 parameter empirical equation is a model equation for elephant, when there is no physical significance of all the constant. So you need to match up between this theory, ideal, non-ideal, reality. So balance everything. So you will get model equation with some error, simple model equation with some error. So at the end, you will add some appropriate factor of safety. So that is the advantage of this modeling. You can say that is the advantage of engineering. Otherwise, in science, so in mathematics, people will study 10-dimension problem also. When reality there is not more than 3 dimensions. Now people are looking at the time as a 4th dimensions. But in mathematics, you will have solution for 10-dimension problem also. So science will not look for reality. So there is the bridge between science and reality is engineering. That is why we are studying so many. So you will have so many assumption, factor of safety, and this thing, and everything will have some importance. Actually, everything accounts for some importance. Is this clear?
Yes, sir. Yes, sir.
Okay. Anybody else has any doubt in this?